C'era questi ganchos che erano registrato il microfono
Julian, just to change the slides, I do with the keyboard. Yeah. Okay.
Welcome to the other sessions. Good talk by Oleg Lisovyi, who will read the tools, connection problems for Heun and Mathieu equations in the quasiclassical conformal box.
Thank you very much, and many thanks to the organizers for inviting me here and for this opportunity to present my results. So let me first discuss some general context. Since the very discovery of the two-dimensional conformal field theory, there have been many connections discovered between this theory and the world of linear and nonlinear ODEs. So the first of such connections was probably due to Zamolodchikov in 1986, who has shown that, who has conjectured basically that the accessory parameter problem for Heun equation can be solved in terms of quasi-classical conformal blocks. So quasi-classical here means the central charge which goes to infinity, just like we have seen in the talk this morning. Then there have been many other things, among which, so the ODE-IM correspondence and the relation between Penlevé functions and C equal to 1 Virasoro conformal blocks. And like most recently, there was another development in this story initiated by Zamolodchikov, where so these people, Bonelli, Iossa, and Tanzini from CISA, so they have conjectured that not only the accessory parameter, but also the connection matrix for the Heun equation and for its confluent versions can be written in terms of the very same object, so the quasi-classical Virasoro conformal block. And so basically what I'm going to explain is that in order to obtain like equivalent formulas, we do not actually need CFT, so this can be the corresponding perturbative expansion of the connection matrix in a suitable parameter can be actually obtained by very standard methods, sometimes old, like 1 century old, sometimes even more. Okay, so just to start with a simple example of this CFT ODE relation. So let us consider the Mathieu equation or modified Mathieu equation. So this is just a Schrödinger equation for one particle in a confining potential, Koch potential. And so suppose that we want to understand how the discrete energy spectrum here depends on the coupling T. Okay, so in the equation you have two parameters, so it will be always the case even when we will consider a more complicated equation. So one parameter, which here is the energy, will so this plays the role of the so-called accessory parameter, and the variable like t, sometimes I will refer to it as time. Okay, but here it's just the coupling. Okay, and so the first case to analyze, which is an easy one, is the case of large coupling. So here, basically, your Koch potential can be well approximated by a harmonic oscillator, and you obtain so here you see the expansion of the energy level, so 8 square root of t. So this is just the first term of the expansion of Koch. So this comes from the harmonic oscillator. This is the first order contribution from the usual perturbation theory in quantum mechanics, and in principle you can compute as many terms as you want. Now, the regime with which CFT is concerned is the opposite one. So this is the case where the coupling is small. So this is somewhat like not very physical, maybe rather counterintuitive. So you have a potential which is like almost everywhere zero, and then somewhere far at minus and plus infinity, it goes up. So we want to understand what are the eigenvalues here. And one way to obtain an approximate form of the eigenvalues is well, let us just discard one of the exponential in Koch. Then the corresponding Schrödinger equation can be solved exactly in terms of Bessel functions. So this is if you have a physical background. So this example is already in Landau-Lifshitz. And so if you want, for example, the solution which is decreasing at plus infinity, so the solution is this the so-called Hankel function. And so this is very rapidly decreasing, as you see. And so one may expect, one can even argue, doing various estimates, that this solution actually remains a rather good approximation of an actual solution of the Mathieu equation for, well, for all positive x, but also for x which are not too negative somehow. So for x's where you do not yet feel the other exponential, okay? And so now in the first approximation, you can impose as a quantization condition. So our potential is even, right? So we have the wave functions which are rather, which are either even or odd. And so we have this quantization condition for odd levels and even levels. Okay, so this is very crude asymptotic estimate. And so when coupling goes to zero, so then, for example, from this equation, we obtain an equation of this form, which I believe we have also seen this morning. At least a very similar equation appeared this morning. Yeah. Okay. So then this has to be solved for small t, and well, the leading asymptotics of the eigenvalue is the upper formula there. This is what you get basically when you just replace this ratio of gamma functions by 1. Okay, and then you have many other corrections that you can compute. So basically, you have here a double series for energy levels. So a double series in powers of both logarithms and t. Okay, and so for example, solving this equation implies that you take into account already an infinite number of these logarithmic corrections. Okay. Well, and now physically, what is going on? Physically, this is the spectrum of an infinite well. of length log of square root of t, which is once again rather intuitive. So if you look at the potential, so basically you say that your potential is 0 everywhere, and then somewhere starting from coordinates where these exponentials become comparable with square root of t. So there you start to have infinite walls, and so this gives you this leading approximation. Okay, so now what is the CFT answer provided to this problem of discrete spectrum? So the CFT answer is given by this formula. So the accessory parameter of Mathieu is obtained as a derivative of some mysterious function of two variables t and sigma, called quasiclassical irregular Virasoro conformal block. So if I were completely precise, so actually Zamolodchikov didn't do the example of Mathieu equation, so he had this formula for Heun. But if he were interested in the time at Mathieu, he could write the same answer. And now, but our energy has to be a function of the coupling, right? So we have to put here some specific values of sigma, and the specific values of sigma, they are determined by a quantization condition, which involves, once again, this very same function, w. And so this function is actually, if you have never seen it before, you should think of it as being some power series in T. So this is, like, by definition, a perturbative series. There is no non-perturbative definition. So the coefficients of the series you can compute for any given order. But there is no formula, explicit formula for this coefficient. You have to work. For example, if you want order 20, then, well, this will be a certain computation. Yeah. Now, so this is the structure, okay? So you have, so what you have to do in order to compute En. So first, you have to, so suppose you plug this perturbative series into this equation, you solve this for sigma, and then you plug the corresponding values of sigma into here. And now, if you compare with the formulas that we have just seen before, so suppose that this W of t is 0. So just neglect this term here and this term here. Then, so this is nothing but this equation. Okay, so basically what I am telling you is that somehow this variable sigma, it encapsulates all logarithmic corrections, and the series in T is precisely given by this quasi-classical conformal block. Okay, so now just one slide in order to convince the mathematical part of the audience that W of T actually has a definition. Okay, so so the starting point here is the Virasoro algebra. So we take a highest weight module generated from a vector delta, which is so annihilated by the negative part of the algebra. It diagonalizes the generator L0. And then we are looking for the so-called Whittaker state lying in this module, which is a joint eigenstate of the creation of the annihilation part of the algebra. So think of something like a coherent state for creation annihilation operator. So this Whittaker vector is a kind of the simplest example of a coherent state if you replace this Heisenberg algebra by Virasoro. Okay, so you have all generate Virasoro generators with indices greater or equal than 2 acting by 0, and L1 acting by some number, which will play the role of the coupling in our problem. Okay, and so in principle you can compute the expansion of this Whittaker vector in powers of t, and compute well, this function, which is essentially the norm of the Whittaker vector. I could have fixed normalizations of delta and w in such a way that f would be just this guy here. Okay, and so this is a certain series whose coefficients can be computed using Virasoro commutation relation. Now, what does the word quasiclassical mean? So it means that in this conformal block, we have to rescale everything. So we have to rescale this eigenvalue. We have to rescale the conformal dimension and the central charge. So all of this is sent to infinity in a certain correlated way. And well, already this is like a conjectural part that this limit exists. But okay, you can compute it order by order and convince yourself that, yeah, so the limit should exist. And so the statement is that so the derivatives of this function with respect to these two arguments, they are relevant for our spectral problem. Yes.
Then the safety argument tells you that the series should converge for finite t, but what is the ratio or what is the radius of convergence?
I'm not sure CFT has any arguments for convergence. So in the regular case, yes, you might believe, although still I don't think there is a proof. So in the regular case, there is a belief that the radius of convergence should be equal to 1. So here one may believe that the series here is uniformly and absolutely convergent in the whole complex plane. Once again, for this usual conformal block, non-quasi-classical one. For the quasi-classical one, we do know that the series is has a finite radius of convergence. And this is very old. Let me put it in a different way. So if you look at this formula, so accessory parameter given by the derivative of w. So this accessory parameter, so this function was studied by people like Mathieu and Heinz like a century ago. And so they have already known that so this has a finite radius of convergence, depending in principle on sigma. But I mean, there is no analytic result for that. Okay, just yeah, so some finite non-zero radius of convergence.
Is always 0 and 1 and comes from 0 to infinity, and it has some singularities on this interval.
Okay, actually, maybe one can say something about the radius of convergence of this function here. So in some specific cases, it is very easy to analyze. We did it for c equal to 1, for example. Then there was a paper by Alessandro and Giulio where I think they have done something for the generic central charge. But once again, so the convergence of this does not have much to do with the convergence of that. Okay, and here once again we do know that the radius of convergence is finite.
What is the regular?
A regular case. Yeah. So regular case. So there you would have a matrix element of a product of vertex operators. So I didn't want to introduce the vertex operator, is why I consider this simple situation where I can actually give a compact definition of what this guy is.
What is it?
Irregular, well, in the
Without weight occur.
yeah. So in the regular case, the relevant conformal block would be something like this. You have two highest weights, delta infinity and delta naught, and you insert here two vertex operators, one located, say, at t, one located at 1, delta infinity, delta 1. So it would be this function. But once again, I didn't want to explain these letters, which but you can guess, like at the level of differential equations, what does it correspond to? So here we have Mathieu equation, which has like two irregular singularities of Poincaré rank 1/2. So this corresponds to this Whittaker states here. And in the regular case, so the vectors that you have in the story, they correspond to Fuchsian singularities. Okay. Okay, so now I would like to explain quickly this conjecture by people from Trieste. So now I rewrite Mathieu equation in the form that I like. So just as I said, so this is a rational potential, two irregular singular points. And so this parity symmetry that we had for Koch potential is this symmetry here. Now, this equation admits a pair of formal solutions of this form, and the actual solutions are determined by the requirement of the asymptotic, of being asymptotic to that inside certain sectors. So this is a basis of solutions associated to singular point at infinity. This is, in a similar way, a basis of canonical solution at 0. So these guys basically are fixed uniquely by the exponential decay inside these sectors. And then, so this exponential asymptotics that we have seen on the previous slide, it continues into adjacent sectors, but now it's growing, right?
What was changed about y?
What? As you may guess, so it is z equal to exponential of 2x up to some factors. Yeah, the most naive. Right, and now these two bases of solutions, they should be related by a constant connection matrix, which is convenient to parameterize in this way. So this form of the connection matrix basically follows from this discrete symmetries and from the expression of Wronskians of pairs of solutions associated to the same singular point. So these are very easy to compute using the asymptotics. So you can parameterize this connection matrix in this form. And so here you have two parameters, as you see. So this sigma variable is the parameter that has already appeared before in the conformal block. So this is the eigenvalue of monodromy around, well, let's say z equal to 0, but it's the same for z equal to infinity because there are only two. And so this guy is given by the Zamolodchikov conjecture that I have explained to you before. Okay. Now the proposal of Bonelli and others may be collapsed to the following statement. So the parameter eta in the connection matrix is a derivative of this function w with respect to sigma. And so I will refer to this as a Trieste formula for Mathieu equation. So,
maybe collapse.
yeah, because like originally the connection formula that they have written is not as compact as that. So yeah, yeah. So this is like a simple reformulation in a nice parametrization of the connection matrix. So this quantization condition that we have seen before, so given the energy spectrum, basically it becomes just the statement that the parameter eta here is integer. Okay, now a few words about the Heun equation. So Heun equation is a generalization of the hypergeometric equation. So in the hypergeometric equation, you have, well, Schrödinger equation with this type of potential. And so what is important to like emphasize here is that, so basically we need to look at the singular points of this quadratic differential. And for hypergeometric equation, we have three second-order poles. So two second-order poles, this is just Euler equation. And now to every singular point, so these singular points corresponding to second-order poles, they are called Fuchsian or regular singular points. And at each of these, one can introduce a basis of Frobenius solutions, actual Frobenius solutions where you expand in integer powers of z and not like in this ODE-IM story. I don't, by the way, I don't quite understand why do you refer to those as Frobenius, but well, anyway. Well, because you have something like Puiseux series, right? So it's, I mean, this is not an entire series that you have there.
But there is a series in entire function, not complex variety.
Well, anyway, so yeah, and so now the connection problem for hypergeometric equation relates these two Frobenius bases by a very simple formula involving gamma function. So this is very classical story. Now we add one more Fuchsian singularity to this story. And a consequence of that is that now in our potential, we have one extra term with a parameter epsilon here that does not influence the local behavior of solution. So this is called accessory parameter. So this is the counterpart of the energy in Mathieu. And the counterpart of the coupling in Mathieu equation is the position of this fourth singularity that we have added. And for convenience, we will assume that the singularity lies outside the unit circle. Okay. Now, we can also introduce the space of monodromy data for this Heun equation. So it consists of a four tuple of SL2 monodromy matrices that multiply up to 1, whose eigenvalues are fixed. And so these matrices have to be considered up to overall conjugation. So it is not very difficult to convince yourself that this space is actually two-dimensional. And there are different ways to introduce local coordinates on it. So one way, one choice of coordinates. So this could be this epsilon and t, which appear in our differential equation. Another possibility is to use, for example, this trace functions. And so you see, this is this, once again, we have this parameter sigma, which appears. So now it's the monodromy around a pair of points. And depending on the cycle that we choose, so we can have different sigmas. Yeah.
Which means it will be a local coordinates of M.
Okay, so this is the Riemann-Hilbert correspondence. Yeah, of course. Yeah, so this is very transcendental description, of course. So you have this equation data on one side, you have monodromy data on the other side, and then going in this direction as well as in this direction is complicated. But this is basically what this homological conjecture achieves. Or almost. So we have this direct and inverse problem, but what we can also do is take one parameter from the left, one parameter from the right, and determine the rest in terms of these two. And this is precisely the statement of this homological result. So the accessory parameter as a function of t and sigma is given by this derivative of the quasi-classical conformal block. So this is, once again, some function. You should look at the CFTs as a kind of black box, which produces you a series for this W, okay? But then you can also compute this accessory parameter expansion in a purely mathematical way. Well, basically solving some recurrence relations and just check that the homological conjecture produces you the correct result. Okay, so now what is the Trieste formula for Trieste variant of the Trieste formula for coin? So here we have two bases of Frobenius solutions. And the connection between the two is given by, well, this matrix, basically expressed in terms of a single function. And this function, once again, it is expressed in terms of derivatives. But now the derivatives are taken with respect to local monodromy. So in Mathieu's story, we have already seen differentiation with respect to like time or coupling, with respect to the this non-trivial parameter on the space of monodromy data, like sigma. So here, to get the connection coefficient, we also have to differentiate with respect to local exponent. Okay. But again, so this gives you a certain practical way to compute a series for this connection matrix in powers of t, basically, or powers of 1 over t in this case. So what you have to do is, well, you generate this series expansion using your favorite method. Then you compute the expansion of this composite monodromy by solving this equation. And then you plug the corresponding values of sigma into this formula. Okay. And you may see that when you do that, you will have to expand. So suppose that we take the logarithm of this guy and expand. So there will be, so sigma is appearing both in gamma functions and in the coefficients of W. So this will basically produce you some series in 1 over t with some rational coefficients, and this will produce some polygammas, right? Because you have to differentiate this at some point. And well, the formulas do not look like super nice, but this is what you get. Yeah. So when you have your the parameters of your equation, so this is the series that you compute for this connection coefficients. So now the question is, how can we check this? Or how can we compute the connection matrix without using CFT? Okay, so maybe I will be quick about this because I have presented this method a couple of times already. So, this method based on the so-called Schafke-Schmidt formula is based on a very old idea that you can actually detect the singularities of a function by looking at the asymptotics of its Taylor coefficients, basically. So the basic example is this. So just take this function over here. So this is its Taylor series around 0. And then, so this coefficients, they have this fractional power behavior in k as k goes to infinity. And so you see that, so this branching appears as a power of k. And basically, the coefficient 1 over here is what multiplies this fractional behavior in the expansion of in the expression of our function, which was analytic around 0. Okay, so this is basically the whole idea. So what you have to do is to take the solution of your differential equation, construct its power series expansion. So you have some kind of recurrence relation for the coefficients that you can compute. Look at the asymptotics of this of the solution of this recurrence equation as k goes to infinity, and so the limiting value will give you essentially what you want. So now let me make this more precise. So this is the basic statement, Darboux theorem. So you start with a function which is analytic around 0, and you somehow know that that you have only one branch point z equal to 1 inside a circle of a radius strictly greater than 1. And suppose that once again, you know that the behavior of your function looks like this, where v of z and w of z are analytic around z equal to 1. Then the connection coefficient, so the value of this function at z equal to 1, appears in the large order asymptotics of the Taylor coefficients of u. Okay, so this is Darboux theorem. So you can, by the way, use this very easily to compute the previous connection formula for hypergeometric equation. So this is maybe the easiest way to compute the connection formula for hypergeometric equation. And now one can apply this to differential equations where you have at least two Fuchsian singularities like Heun. And the idea is that, well, so here I can put any function which is holomorphic inside a circle of radius greater than 1. So this is just not to spoil this Fuchsian behavior at these 2 points. You introduce these Frobenius solutions. You introduce the connection matrix. And the Darboux theorem in this case is basically the statement here. So it's a more precise form of what I have just said. So the connection in terms of large order coefficients. And now in the context of Heun, how does it work? So basically you take a potential. So this is not exactly Heun. This is the so-called reduced confluent Heun equation, where you have two Fuchsian singularities and one irregular singularity of Poincaré rank 1/2. Okay, so this is like halfway between the Heun and Mathieu. exactly halfway. So if you forget about this term, this becomes just hypergeometric equation, right? And now, so what you do is that, for lambda equal to 0, of course, you know the analytic expression for the for all of the Taylor coefficients. Now, you divide the actual Taylor coefficients by this limiting value at lambda equal to 0, and you obtain a recurrence relation, very simple one, like this one here. And so the connection coefficient is essentially the limiting value of the sequence as k goes to infinity. And this can be computed in various ways, which I will probably skip. So there is some combinatorics involved. This is the end result. So for this equation, the connection matrix admits the following representation in terms of these infinite fractions. So basically, if you want to compute the expansion of this guy in powers of lambda, you have to truncate this infinite fraction at the desired order. The sums that you have to compute over here become some sums of rational expressions in K. So that will produce you like a bunch of polygamma functions and some rational functions as well. And this turns out to reproduce exactly these predictions of Trieste formula for reduced confluent Heun. And for the Heun, it's essentially the same formula, just with more parameters involved. So, and you can check just order by order the validity of the CFT predictions. But once again, the claim is that you don't need CFT anymore to produce the series. Okay, now I would like to tell at least a few words about an alternative approach which works for Mathieu equation. So what is the problem with Mathieu equation? So in principle, we could try to apply the same idea, right? So once again, to look at something like large order asymptotics, but now of the coefficients of an asymptotic series around irregular singular point at infinity. So in principle, this is maybe doable, but we also wanted to obtain a result that would be somehow closer to the original formula by Bonelli and Tanzini, which means that we would rather like to have the expression for the connection matrix not in terms of the accessory parameter, which appears here, so this omega parameter. So the CFT formula looks much nicer if you have here, instead of omega, this composite monodromy exponent sigma. So we wanted to reproduce that, and we wanted to avoid this Schafke-Schmidt approach. And it turns out that at least formally, so this will not be a mathematical theorem, not a rigorous result, but at least formally, it is actually very easy to obtain a perturbative expansion of the connection matrix. So now let me explain how does it go. So you start from, so remember, in Mathieu equation, you have here also a term in 1 over z cube. Now, we introduce this model equation. And if you think, this is exactly what we did at the very beginning when I wanted to obtain an approximation for this discrete spectrum. So I neglect one of the exponentials here. So the solution of that will be given by Bessel functions, which, well, you have two convenient bases, one of which is at this Fuchsian singularity is equal to 0, and the other one at the irregular singularity is equal to infinity. So here you have these Hankel functions that we already had, and you have Bessel functions. So these funny prefactors that you have, they are introduced just to make these solutions asymptotic to what we really want, to this normalization that we have introduced for canonical solutions of Mathieu. And we have a very simple connection formula between this Bessel bases, where, so this is, of course, classical. One thing that should be noted here is that the connection matrix here is periodic with respect to, or almost periodic with respect to this sigma. This will have some importance later on. Okay, and now what do we do? So in principle, I could take my full Mathieu equation and construct Floquet solutions in this form. Okay, so sigma is precisely this composite monodromy exponent. Here we have a Laurent series in Z, so which is a valid expression for the solutions of this equation in the whole annulus, like with the exception of 0 and infinity, right? And we normalize this solution by setting one of the coefficients to be 1. These coefficients can be, so they solve some recurrence relation, three-term recurrence relation following from our differential equation. And one can write an expression for these coefficients, which is suitable for computing this series expansion in the coupling T. Okay, and the accessory parameter is obtained from this equation here, which is basically the result of Mathieu, which produces exactly the same perturbative expansion as the homological conjecture, but which was obtained more than 100 years before. Okay. Now, how to upgrade this to the connection formula? So what you have to do is to just formally expand the Floquet solutions, not in the basis of powers of Z, but in the basis of this solutions of Bessel equations, model Bessel equations that I have introduced. So you see, I am summing with respect to K, and this K is involved in the shift of sigma. Okay, and this guy here, of course, it should be like proportional to the Floquet solution that I had, and the proportionality coefficient can be easily computed. I think I have it on the next slide. Yeah, maybe I go ahead. So, so this is the relation between the standard Floquet solution and the Floquet solution where I expand in this Bessel basis. So here you have like Pohammer symbols, some gamma functions, but the point is that this coefficient has a very easily computable series expansion in T with rational coefficients. Okay. Now I go back. So these coefficients entering into the computation, once again, they are computed by some infinite fractions, more complicated than in the case of expanding in powers of Z, but still very much comparable in complexity. So once again, what I'm doing is like almost completely elementary manipulation. The only like formal point is that, well, I am writing series in Bessel instead of writing series in powers of Z. So it is maybe somehow tricky to look for convergent of this thing. Now, how do we obtain the connection formula? So the idea is this. So we have this expansion in terms of Bessels, but we have connection formula for Bessel. So we can replace this guy by S. So these are Bessel functions G, but we can replace them by linear combinations of Hankels, so these functions psi. And the thing is that now each of these guys is asymptotic to this canonical exponential behavior that we want, which means that in the end, we have here a sum, a linear combination of this canonical solution of now Mathieu equation at infinity. So we have actually a connection formula between Floquet, so solutions in the middle, and infinity. But using the symmetry, we could exchange the roles of singular points 0 and infinity by just this parity symmetry, so this substitution, which leads to this connection formula, basically. So if you rewrite everything, so you have solutions at infinity related to Floquet in the middle, you have this same Floquet in the middle related to canonical solutions at 0. Okay, and if you now eliminate Floquet from the story and rewrite the appropriate linear combinations of this psi's, you can basically make this compact statement that connection matrix is this, and the parameter eta is this ratio. And as I told you before, so the non-trivial guy here, so this epsilon, was something that we can easily compute, easily expand in powers of t, and have a series with rational coefficients in sigma. And well, as expected, this corresponds to the prediction of Alessandro, Giulio, and their students. Okay, so now I come to conclusion. So perturbative solution of the connection problem for Heun equations, and by Heun equations, I mean Heun and many of its confluent versions going all the way to Mathieu. So this connection problem can be solved systematically using this Schafke-Schmidt approach. So this is a rigorous approach, which confirms Trieste formula expressing this solution of the connection problem in terms of quasi-classical Virasoro conformal blocks. And there is an alternative, more simple even way, although a bit formal, to derive the same expansion by expanding Floquet solutions in the basis of appropriate parametrices or approximate solutions of our differential equation. So that's it. Thank you very much.
In principle, you could integrate this expression, the last page, for eta and find w, right? Integrate that as a function of sigma.
Why I would do that? No, okay, so but then I would integrate what I get from here, actually. So what is written here computes this omega squared, which is the derivative of w with respect to t. So I can, yeah, so I can integrate that with respect to t and get quasi-classical conformal block.
In principle, they should be same w. Is it obvious?
Yeah, but no, it's not obvious why if you integrate that with respect to sigma, you get like the same thing that when you integrate the previous thing with respect to t. Yeah, that is not obvious at all. But this is somehow like if you eliminate completely CFT from the story, so this is like the statement, non-trivial statement of this Trieste formula that the connection coefficient is given by the derivative with respect to composite monodromy of the integrated accessory parameter function. And this
It's the derivative of the sigma, the thetas, not of the sigmas.
for Mathieu, there are no thetas, so there you have to integrate with respect to sigma. Yeah. But this statement is actually non-perturbative. So this is not about the series. This is like an actual mathematical statement, which basically tells you that this Riemann-Hilbert map that I have introduced between like epsilon and t and these monodromy parameters, so that so this is actually a canonical transformation, and the generating function of the this canonical transformation is that function W. Okay.
Large T expressions can be obtained in the same method. Well, for Mathieu, I know it's sort of easy, but
For Heun, it's also easy.
yeah, for Heun is also.
For equations between Heun and Mathieu, it's more complicated story. I do not know how to systematically do it.
Can you go towards the last formula for C, the connection matrix in terms of
For which equation?
for Mathieu, one of the last.
Yeah. Yes.
So now the parameters of Mathieu equation are P and sigma.
No, sigma is not actually a parameter. It's like a monodromy parameter, right? So sigma is a
Epsilon, the original.
yeah. So in here, so
you in terms of P and sigma, this is the connection matrix given by the formula, where the sign of 2 pi eta must be computed in terms of this range. This big gamma.
yeah. So this thing, so this is a series in T with coefficients rational in sigma.
Okay. And this series, can you?
The series comes from here.
So this function is what are the identity properties of this function? There is like an expansion somehow. I don't know where exactly.
This is an expansion in T. So you are asking about analytic properties in what? In T?
Well, it's function of the sigma now.
Sigma.
Sigma.
Of sigma in T, yes.
Okay. But like the formula that you in the previous slides has some range of validity depending on the properties of this function, or there is no issue about it. I mean, this is a representation that is
no.
You need, or just for a corner of that. I mean,
I don't have a short answer. So the formula that we obtain by this Schafke-Schmidt method, so it is well, it may be expected to be analytic for every value of T, and it has no singularities in this accessory parameter, which I denote omega. Now, here, there might be some complications related to the fact that I traded this accessory parameter for composite monodromy exponent. And I'm not sure if we can completely avoid these complications. So
we found a concept of this for João. And there is a strange thing. I mean, if you write a series, the series is perfect. But this functional relation that you wrote in the previous slide, it actually defines implicitly some function that seems to be analytic. You have this slide where C1 tilde 1 plus the one that you use to get this C's, right? This functional relation coming from this continuous spectrum.
let me maybe give a different answer. So forget about this expression, okay? So what is the meaning of this epsilon? So epsilon is the basically the connection coefficient between canonical solutions at infinity and Floquet solutions in the middle. Okay, so one can, of course, expect this, and maybe one can prove this to be analytic for every value of t and almost every value of sigma, except for sigma integer of half integer. So there you can have some issues.
Then you can continue later.
Thank you.